I'm Akshat, a third year undergrad student of BS Physics at IIT Kanpur. And today what I would like to talk to you about is a really cool phenomenon that I came across, that is the quantum Zeno effect. Now let's just start talking about it, and if I were to describe quantum Zeno effect in two simple words, it would just be freezing evolution. Now what does that mean? So imagine, let's take a very simple example, and imagine you have a pot of water boiling. Now if you put your finger inside of it at any moment of time, you don't really feel a change in temperature instantaneously. Of course it changes gradually with time, but at any moment of time t, you're not really feeling any change. So it feels like a watched pot never boils. For a quantum analogy, quantum Zeno effect is a feature of quantum mechanical systems that allow a particle's time evolution to be frozen by measuring it frequently enough. The first question that you're probably wondering is, what do you mean by an observation? Now, an observation in quantum mechanics is any change to a system that causes its wave function to collapse to any of its eigenstates. So what happens is, when you make frequent observations, it prevents the wave function to change. It keeps collapsing back to one of its eigenstates, sort of freezing it. Let's take a simple thought experiment. So we take an electron in an upspin, and we have a lot of magnetic fields, tiny magnetic fields that are just going to deflect or rotate the spin by a very tiny amount. But the setup is such that after m such rotations, what you get at the end is just an inversion. So you get a downspin rather than the upspin that you started with. Now what we're going to do is change this a bit. After every rotation of the magnetic field, we're going to observe the spin. So let's take the first instance. We have an upspin. It goes to the magnetic field. It gets rotated by a tiny amount. And when you measure this rotated electron, it has a probability of either collapsing to the upstate or the downstate. Now since it has rotated only a tiny amount, the probability of it collapsing to the upstate is significantly higher than collapsing to the downstate. So what you'll probably observe is that after this measurement, it goes back to the upstate. Now after the second magnetic field, a similar thing happens and it collapses back to the upstate. And so on and so forth until at the end what you get is the upstate again, rather than the expected outcome, which was the downstate. So what you essentially did was, you froze this electron in its upstate by measuring it continuously after each change. And the math supports it as well. I don't think we really have to talk about the maths of it too much, but it just says that the probability of it measuring in upspin remains or tends to 1 after n measurements. Similarly goes for a generalized formulation, as you get an exponential with a minus tau term, which as you tend tau to 0, it goes to 1 again. But the more interesting thing that I want to talk about is that what we have discussed so far is just theory. But what about the experimental verification of it? So in 1990, Wayne and Heinzen actually conducted an experiment by taking singly charged beryllium ions, which had these 3 states. The first one was the ground state, the second was the excited metastable state, and the third was an excited electronic state. Now the first and second state were coupled by an RF field. What happened was, the wave function will keep oscillating between these two, and you measure it by shining a laser beam repeatedly on it. So what will happen is, either the wave function will collapse to the first ground state, or it will collapse to state 2. How do you observe it though? So the observation was that, let's say after your measurement, the wave function collapsed to the first one. Now what will happen is that this ground state, the electron will have enough energy to move to the third electronic state. And now this, when the electron goes up, it will come back down, causing a release of photon, which you can measure, which you can observe as light emitted. However, if the electron goes to collapse, if the wave function collapses to the second state, what will happen is, it will not go to the third state. There will be no more photons emitted, so it will be a null measurement. So that's how you differentiate between a state 1 verification and a state 2 verification. Now what happened was, we started from the ground state, and when you shine repeated lasers on it, what we observed was, if you shine it only once, the probability of it transitioning to state 2 is extremely high, almost 1. But as you keep on increasing the number of laser shines on it, the probability of it actually transitioning keeps on decreasing exponentially. And as soon as you hit 64, the probability of you actually observing it on state 2 is almost 0. So the probability of it being at state 1 is almost 1, obviously. So you have essentially frozen the state from which you had started. And that's how you experimentally verified the Zeno effect. However, there are certain controversies related to it. The main one being, what is an observation and how is it different from a perturbation? So what you're doing in measuring or observing quantum Zeno effect is you're essentially coupling the system and the observation together. Now what happens is, because you're observing it so frequently, these are not subtle measurements anymore. As compared to classical analogy where measurement doesn't really affect the system, in a quantum state, observation actually impacts the system. So there is a debate that in the experiment that they conducted, the continuous bombardment of photons was not a subtle measurement, and the act of watching actually changed the watched. And so there is this big debate as to whether you can essentially measure Zeno effect or not. And a recent study showed that with the right type of perturbation, you could actually speed up the wave function rather than freezing it, which is called the anti-Zeno effect. So I would leave you all with this question and you all to think whether the wave quantum Zeno effect was verified was actually true or not. And just think about it. Yeah, that's it from my side. I hope this was a good time. Thank you.